Hi, welcome to this session where we're going to talk, or I'm going to talk about some things I learned analyzing profiles of code programs to make performance improvements. I got to work on a couple of these problems in the past years, and I want to share what I learned. The basic structure of this call is I'm going to very briefly talk about what profiles are. And then I'm going to demo a little bit with the Google Cloud Profiler, click around and show what I look at or what I see. And then I'm going to look at a demo app I made on my MacBook, so to show how you can use profiles in local development, because I think that's also very useful. Okay, so I'm going to start by sharing my screen. See, share screen. There we go. So, yeah, about profiles. Profiles are kind of recordings you make of what a process is doing, and they are based on snapshots. And there's all sorts of different profiles you can make, but the kind of profiles I'm going to be talking about are mainly CPU profiles and allocation profiles, and I'm going to mention heap profiles sort of as an honorable mention, but I didn't end up using heap profiles that much in what I looked at. So heap profiles are also the easiest to explain. So a heap profile is a snapshot of all the objects that are on the heap of a running Go process. And for each object, you can look at its size, and you can look at which function made it. And if you add that all up, then you see the total size of the heap, and you see the size that each function contributed to the heap. So it's a single snapshot of the process. Another kind of profile with an allocation profile, you need two snapshots, and they're based on counters. So every allocation will increment a counter saying this function allocated this much memory. So if you take a snapshot of that, then you get the counters that reflect everything that happened until that point in the life of the process. So on its own, those numbers are not very useful. But if you then wait a while and take a second snapshot, then you can take the difference between those two snapshots. And then those show you how much was allocated in that time period. So that's, and then it gets interesting, because we don't you cannot compare processes because they will have different running times. But if you compare differences, you can compare across different processes. And finally, CPU profiles. So this uses one snapshot, this uses two snapshots, and this uses thousands of snapshots. So with a CPU profile, what you do is you, for a fixed period of time, you run a timer at a fixed frequency, and every time the timer goes off, you freeze the entire process, and you look which functions in the process were running on the CPU. This is bad because it slows the process down, but you do it at a frequency where users hopefully don't notice. And yeah, so then you get thousands of profiles, but then you can summarize them by looking at for each function that is in one of these profiles, like how often it occurred. And then again, you can associate a number with the function, and you can say this function was so many % of the time this function was active. So those are three kinds of profiles. Unless they're okay. Question? Any question? Okay, then I'll go and show you some profiles, make it less abstract. And let's look at the Cloud Profiler. I don't know who at GitLab exactly has access to this. I think Scalability did a project to give developers access to this, but I don't know if all developers have access. If you are a developer and you want access to these profiles, go to the Scalability channel and ask if that can be organized, because they're useful, and you only need a browser to look at them. So I just opened this page, and it defaulted to going to Gitly, which is one of our Go applications, of course. And this thing, what we see here, is called a flame graph, and it's a visualization of a profile. And it's a very nice visualization. And I will only be talking about flame graphs in this demo. There are other ways to look at profiles, but I'm just going to focus on flame graphs. When you use this profiler, there are a couple of things to watch out for. You want to look at the app you're interested in. You want to make sure you're in the right environment. Usually that's production because that's where interesting stuff happens. And you want to look at the time here of the profile. So 7 days is a good time because that's a full week, and there are often patterns in traffic that you have like the weekdays and you have the weekends, and this will average over all of those. So 7 days is a useful window. If there was some sort of incident, you know, something happened at a certain time, then you can try to narrow down on that time. But in experience, in practice, I find it difficult to hone in on incidents with this interface and this tool because it collects too much data from too many different processes. So you cannot always find the process where things went wrong. So it's more for general traffic to know like what normal traffic is or what happens normally that you can analyze here. But think about the window. 7 days is a good window. 1 day is also a good window if it's not Monday, because on Monday you do 1 day into the past, you may capture part of Sunday, and Sunday is not normal, and you don't see normal traffic. But if it's Tuesday or Wednesday, you do 1 day in the past, then anything that occurs on a 24-hour cycle will be included in the visualization. So that's useful. And if you happen to be looking at a time of peak traffic, then 1 hour or something like that can also be useful. But yeah, usually I would go for 1 day on a weekday. But I looked earlier, and this 7-day profile has some interesting data in it, so I'm going to keep it at 7 days. The profile type here is CPU time. And in this interface, you can also look at the heap contention. That's about mutexes. I'm not really sure what the threads profile shows. This is the allocation profile. So the profile type is important. Other thing that's important is this thing, the weight box. So right now we're looking at an average. And if you want to understand performance problems, it's usually more interesting to look at the high quantiles like the P99. So here you can say top 1%, and then you see the outliers or the weird behavior. And lucky enough, in this thing, we have some interesting weird behavior so one thing to notice here is that says 128 seconds. I'm not sure for how long this profiler runs, but this is the higher this number is, the busier the process was over the window. So if this was a 30-second profile, you have 120 seconds plus of samples. That would mean that the process ran on 400% CPU for 30 seconds. If this is a 10-second profile, this would mean 1200% CPU. Because it's only one profile, but I think 1200% CPU is unlikely for a GitLab server. So it's probably a 30-second profile. If we go back here, like here, it says the average was, what was it? 7 seconds. So if that's a 30-second window, then that's a quarter. That's 25% CPU. That's very low. So anyway, this profile was captured when the process was very busy doing something. And something that immediately stands out to me because it's become a pet peeve of mine is this. This is the part of the garbage collection process of Go. And I see that because, well, runtime means it's part of Go itself, and GC means garbage collection. And whenever you see this, there's a lot of garbage collection going on, and that is suspicious. What's frustrating is that if I look here, oh, actually, no, I can't find it. So this is garbage collection, cleaning up garbage. And this one down here, runtime make slice, is making garbage. So it's allocating, malloc means memory allocate. So it's allocating memory. And together, these things are creating a lot of work. And the reason I'm really not a fan of seeing this is that when the garbage collector is very busy, this spills over across all Go routines. So if one user is doing something where they're creating a lot of garbage, and if it would only affect their one request, that wouldn't be so bad. But the garbage collector is shared across all Go routines of the process. And if the garbage collector gets very busy, then all Go routines slow down. And that's bad. It's especially bad on a GitLab server because there's one process that is a gatekeeper to all the repositories on that server. And if that gatekeeper slows down, then access to all the repositories on that server slows down. Okay, so this is an interesting profile from across 7 days. I have no idea when this happened. I can see that here. So this is a big downside of using the cloud profiler. I know something was allocating a lot of memory because there's lots of allocation here. So I can look at the allocation profile and note that it first switches back again to this average. But then if I go to the top one, I see 12 gigabytes, which is also a lot. And maybe this is for the same process around the same time, maybe not. You don't know because of how this tool works. So again, that is a downside. But to me, this is a clear hint what might be going on, and actually know that this is a problem because we've fixed this problem, and I'm surprised that it's happening again. Because what's happening here is that somebody is fetching data from a Git repository with SSH, and it's going through gRPC. So it's using this send message function, and that is allocating memory. This means that somebody was downloading 12.8 gigabytes of data, or I've heard say 12.35. And the really bad thing that gRPC does is that it then allocates 12.35 gigabytes of memory to do that work, which is unnecessary. So
I don't know if
yeah.
I don't know if you wanted questions as they occur.
No, I asked them in the middle because I'm just going to keep talking. Yeah.
Sure. So it's not clear to me. So we're looking at a time span of 7 days, but is, for example, the data on this fire graph a single 30-second, 10-second window?
Yeah, because it says here one profile.
Okay. Oh, okay. So when you go to another percentile, you navigate and you can switch between them?
Yeah, so in the top 1% is just one profile, but this average across everything is 32,000. And if we look at the top 10%, then it's still dominated by this. So there's two profiles where actually this is 12.24, 12.6. So I guess this is just dominated by that one profile. Like out of the 32,000 in this query, one is really, really, really bad. And if you look at that one in isolation, you get this 12.79 number. And the moment you start adding more, it dilutes down the size because it takes an average. So the average of 12.79 and a smaller number is going to be less than 12.79. So it's going to keep creeping down that way.
Got it.
But yeah, this is 32,000 profiles over a week across, I don't know, 100 processes or whatever. So where is this one profile from? You can't see. That's the downside of this tool.
Got it. And I guess I hadn't seen the label that kind of answers my question, which says average over 2 profiles. So this is a combination of those 2 profiles.
Yeah, exactly. You can see it in here. And the nice thing about profiles is that even if you have profiles of different processes at different times, you can throw them together and make a combined profile. So you can naturally merge them or add them up. And that's what this tool is. That's what is nice about this tool, because you can have an arbitrary number of Go processes that are feeding into the cloud profiler, and it will add it all up for you and make a pretty picture so you can see what's happening across all of them. Yeah, so this is something where we see this is probably the same one as the top in CPU time, because I know from experience that this is not normal. So this means that there's a lot of allocations happening. Now, another question that I don't know is, what is exactly the retention window of this data? If you want to share this with somebody who doesn't have access to the profiler, and I just found out like 2 weeks ago or something, you can download these things because there's a download button. And this is a segue to how you open these files on your local computer, and then I can start showing things locally. So if we have no more questions about the cloud profiler, I'm going to download this file, and then we're going to be in local computer land.
My only other question was, where are the services defined for this?
This goes via LabKit. So LabKit, I guess it reads the name of the bind. No, because if you look here in this dropdown, you see things like Workhorse API, Workhorse Git, Workhorse internal API. Those are not names that exist in the binary. So I think we have config somewhere on GitLab.com that says this process should call itself this when it talks to Cloud Profiler. And knowing LabKit, I expect that this is an environment variable we set somewhere, and then these co-processes start connecting to the Cloud Profiler and uploading profiles there. Yeah, so there's a whole list here of things that are connected to this and where you can see differences in behavior.
Okay.
Okay, so I'm going to did I download this already? I'm going to download it now. Save this and open it locally. Let's see, terminal. And this was called profile or something. A nice thing, now we get to doing this locally. The nice thing is this stuff is all built in to Go. So if you have the Go command on your computer, you have a whole lot of tools for doing this stuff, which is really neat because that doesn't, like, I don't think Ruby has all this stuff built in. And the stuff related to profiling is under Go tool pprof. And you can get a kind of, you can pass it a file. So this file is called profiler GitLab something. And I have more than one, but this one is from 04. There. So if you do this, you get a kind of command line interface that I don't understand. Sorry, I'm sure this is useful if you know how to use it, but I don't know how to use this. But you can also do this minus HTTP, and then you need to give it an address. And if you give it the magic address colon, it will figure out a port for you. No, what am I doing wrong? No host and request URL. Localhost. What am I doing wrong? Oh, wrong spot. It needs to go here. Minus HTTP equals colon. No, what am I? Okay, now okay, it says profiler HTTP. I hate this thing when you have a line ending that is wrong and you try to there. So if you do this right, then what it actually does is it starts a web server on a random port, plus it tells your browser to open the URL. So that's really convenient. And now you get this web app, which is built into the Go toolchain. You get this graph. I don't understand how to read this graph, but here there's view, and you can say flame graph. And now we have the same picture again. It looks slightly different, but the same data is here. So yeah, if you want to share one of, so say you're looking in the profile, you find something interesting, you want to share it with people, you can just download this file and open it like this. And like the file is not very big. It's what, 91 kilobytes. So you can just attach that to an issue. So that's useful. The next thing I want to do is to look at a demo app I made that actually shows this problem I was just talking about with the allocations, and then collect the data locally. Because the next step for me in these projects I've worked on was to go from something doesn't look right in production. Here are some cloud profiles that give me a hint of what's wrong, and then try to reproduce it locally. Because if you want to do something about it, you need a local reproducer. You can't just hope you fix something and wait for it to be deployed and then look for another profile and it does needle in the haystack. So so the demo app, and this is public, so you can look at this later if you're interested. I tried to document it, or this is meant to be a toy that you can also explore yourself. So what this is, I took the Hello World demo app from the gRPC repo, and so that's just supposed to do hello request with your name. So you say hello request Jacob, and then it says back in a response, hello Jacob. That's what it does. But I hacked it to serve a stream of data instead, because that simulates what serving data from GitLab does. And for that, I made a little internal thing that pretends running a Git process by opening dev0 and copying bytes out of dev0. That's not really what a Git process does, but that's sort of what Gitly does, because Gitly doesn't know what the Git process does. And to have some control over this, I can say the total number of bytes it should read, and it should do it in blocks of a certain size. So this is kind of like DD, DD if it's dev0. That's what this is. And then I plug this into the Hello World demo app. So this has a handler, and then this thing is called get. And the for incoming message has the total and the block size. And then it calls this thing with a writer, and the writer implementation is down here. So what the writer does is that it has a message embedded, and it clears the message, and it sticks the bytes that the Go wants to copy into this thing, and it sends a message. And this is a very simple way to send a byte stream through gRPC by wrapping it in messages, and it's actually exactly what Gitly does. And I want to say used to do, but it now also does something better, but it also still does this. Yeah, and then this is just pretty much what was in the Hello World demo app. And then the other side of this is a command line client app that makes the connection. And in this one, I already added some profiling code, but we're going to ignore that. This dials to the server, and in a loop, it receives these replies. It does something with the data, because otherwise, don't even know if it consumed the whole response. But it throws the 0 bytes away, and then when it's done, it exits. So this is really, yeah, this is what this does. And yeah, so now say we want to profile this. Well, before we even profile this, we can time this. So over here, oh no, this Zoom thing is in the way. I have this greeter server running, and let's see, I put in the README how to. We look in here, okay. This will download 5 gigs, I think. Yeah, 5 gigabytes of data. If we just run that with time, then we see that it takes, where is the real time? Elapsed. That took 8.51 seconds. Now, for the server side, profiling a Go server process is pretty easy, because there's a nice feature in the Go standard library where you can turn on profiling in the HTTP server. So what I did here is that I imported this library as a blank import, so I'm not using any symbols directly. And I start an HTTP server on an extra port. And then if you make an HTTP request there, you can download profiles. So how does downloading profiles work? Well, one thing you can do actually is to browse this port. So if I do that, and I need to use a funny IP here because this is a virtual machine. I get an error, but if I go to the magic URL debug pprof, then you get this. So this web app is now built into the server process. And now you can look at things like what are the Go routines that are running and what are they doing. So this is fun, but this doesn't give you a flame graph yet. So to make that work, I had to write a script for myself, and I put it here in this repository as pprof record. And what this does is it does a bunch of curl requests to download files from this special magic debug pprof address. And then once we have those files, we can view them with gotool pprof. So let's see, let me just run the script now. And to make it more interesting, we should do something with the server. So I'm going to say, I'm going to make a function, and that does this. So it's easier for me to repeat it. So if I do this now, it's doing one of these requests again. You can see the request coming in here. And that takes about, here it takes 7.8 seconds. So let's do a profile for 10 seconds. And that is, you need to ignore this U that has to do with my plan 9 setup. So if I do this now, I think it's going to record. No, I need to say the port. That's the port. Now it's recording. I'll run the client here. And this should take 10 seconds. Yeah. So what this script now did is that it made a directory and it's named after the host name and the port. And I did this on the 26th. So it's this directory with a bunch of files in them. And now how do you open them? Well, if you do, if you just want to open one directly, you can use gotool preprof. But if you want to do a look at the allocation profile, you need to do a difference between these two profiles. So I made a script for that. That is the preprof open script. So it really doesn't do much, but it uses this minus base flag if you want to do a difference. So if I want to open let's say the heap profile of this thing, and this was here, and it's 26, and yes, magic. I can click flame graph and I can see that this thing didn't do anything. Why didn't do anything? Okay, this is not the profile where the client was running because this doesn't look right. But I can open the profile. So the if you have a server process, you can either get this debug pprof into your server process, like if it's an HTTP server, or you can have a dedicated port, and then you can download the data from debug pprof. And if you then have a benchmark script that exercises the server or that does the workload that you think is interesting, you can record during that, and you can also record multiple samples, because I just recorded both allocations and CPU. But I need to do this one again because this was not the right profile. Why is that? This really makes no sense. Let me try to record again. So that's the profile we got. Look at the CPU profile this time. Okay, now there is stuff. And because I knew that gRPC would misbehave, look, here's the garbage collection stuff happening again. And if I did it right this time, I can also open the heap profile. Oh, now I know what I did wrong. I looked at the heap profile and the heap profile wasn't interesting. I started this call by saying the allocation profile and the CPU profiles are usually interesting for me. And the heap profile wasn't interesting here. So if I look at the allocation profile of this one, then we see that this thing allocated 5.7 gigabytes doing that job. And that's bad, which is the point I was trying to make. And what's nice about this is that I went from, okay, I see something wrong in production. I now have a reproducing example, or what I think is an example with the benchmark. And now if I capture profile data from that test setup, I know that the heap profile and the CPU profile go together because they were captured at the same time when they're in the same directory. Like, there's no doubt about that. So that is very useful. Another part of what is going on here is actually the client process, and the server. It's easy to go to an HTTP URL on a server and download data, but for a client, you have to do something different. there are two options that I like using. One of them is to use perf, which is a Linux tool that actually profiles the entire server, but it will, while it does that, it also profiles your Go apps. Or you can add instrumentation hooks to the binary, the client binary, and have that write a profile to your disk. I'll show both approaches. So to do it with the client binary, the advantage of using the client binary is that it also works on macOS because perf is a Linux tool. But to make that happen, if we look at the code again, I had to add quite a bit of code in the client, so it's a bit annoying. So it takes an option for the directory or the base name of the directory where the profiles go. And then if that is not empty, then it creates a name. So it creates a directory name and writes a profile for the allocations, snapshots. And it defers that at the end of the main function, it writes a second profile because for allocations, we want to take a difference. So we need a before and after. And then it starts a CPU profile. Sorry, that happens here. It starts a CPU profile and that then runs in a Go routine. And we also defer that stops. And then we go into a function where the actual work happens. But this setup code is much more than what you need to add compared to when you're adding this to a server process, because then you just need to make sure there's an HTTP port somewhere. You include the package and everything is there. And here I need to run make dir to create a directory, create a file, look up the profiler, and it's more verbose. But this is this will also work on Mac. That's the good news. But my preferred solution, and this is also why I use a Linux VM, is to use perf instead. So let's see what that looks like. I also put a script in here that runs perf record. Let's see if I didn't mess anything up. So if I do this and I wanted to say do it for 10 seconds, and then I run this benchmark again. So this is running sleep 10, and it's looking at all CPUs while it does that, and it creates a profile 99 times per second. This machine has, how many cores does this machine have? I think it has 4 cores or something. So that is 12,000 profiles it's really creating. Okay, now I have that profile, and that is text data. And to look at that, I need the scripts for creating flame graphs from Brandon Gregg. So those are, if you search for flame graph Brandon Gregg, then there's this repo, and it has some Perl scripts in there. And you could just grab a couple. You need just a couple of them to convert this onto a flame graph. So what I do then is that I also have a script in there. Did I make a script for this? No, I didn't. So now I need to copy this file. Wait, I actually have I'm going to do something. I'm going to redo that. I can actually do perf records over an SSH tunnel, so that will work better. And the port I need is this one. And the machine is this. Oh, I don't need a port. That's because it's the whole machine. Okay, start the benchmark. So the idea of this script is, and I use this to profile production servers. So it will SSH to a production server and then run sudo perf record on the production server and send the data back to my machine, all in one go. And now I have another script here which will open that. So that was 192.168.10, and it's from 2023. And it's 426. This, okay. This is a perf flame graph. And the nice thing here is that you can see that the server was busy, which we also saw appear in the CPU profile. So this picture is the same as this picture, more or less, but we can also see the client, and the client was actually even busier than the server. And if you're trying to look at a if you try to look at the system level, what is going wrong, like you know that GitLab as a whole can do something fast enough, and you don't know where it's going wrong. Something you can that is worth trying is to take an omnibus VM, make a reproducing script that does something on the omnibus VM that recreates the problem, and then just use perf to capture everything on the omnibus VM, and then you'll see where it's spending CPU time. Like maybe it was busy in Postgres, and you would see Postgres here, and you can see with perf you can just capture everything on the box. And the nice thing about omnibus is that it puts everything of GitLab on one box, so you only need to perf that one box, and you can see what's going on. And yeah, working with perf, like you need to manually create the flame graph SVG, but it's less setup work than adding all these hooks into a client binary or into another binary, say, go write a profile here. So this is actually my preferred thing. Go ahead.
I was going to ask, you mentioned that you had shared this script somewhere, or?
Yeah, it's in the repo, the demo repo. So the recording script is in here. I should also add the script that creates the flame graph, but it's not it's not very exciting. It's you need to perf script output, and it needs to go through stack collapse and then the flame graph script.
Got it.
But I'll add that script too. Yeah, and that's one of the reasons I want to do this, is to just show what these tools can do and share them with everybody else. Yeah, so perf is if you can work with a Linux box, perf is actually very nice to work with, because Go out of the box gives perf all the information it needs to just see what's going on. And another nice thing is that at some point Go calls the kernel, and if you have like, sorry, zooms in the way. Here it does, it wants to do a write, and then it says syscall 6, which probably means it's a syscall with 6 arguments or something. And then what happens? We don't know. Go doesn't know, because Go stops here. But if we look at these writes here, where is this? It's not here. It happens in another Go routine. The writes are, oh, they're here. Yeah. So here, here's syscall 6. And now all this stuff is the Linux kernel. So you can see that too with perf. Really cool. It's not always relevant, but like if you see a write here, you don't know what it's writing into. But then if you go up the stack, then you see it says inet TCP, and then you know, oh, this is a TCP socket. So if this was a pipe or a file or Unix socket, then these functions at some point would look different, and then you can sort of work backwards and guess what it is. Yeah, go ahead.
When you're looking at this view where you have the whole frame graph, like what is your intuition to like what looks out of place here? Like, how do you know that something it's taking too much time instead of it's just a heavy process and it's taking the right amount of time?
Yeah.
Like, what do you zoom into?
That is a very good question, and the problem is, part of the answer is intuition. So I think anything outside system calls is suspicious. Actually, there's one step back. So there's and this is something I had to learn, and that was really eye-opening for me, was to look at other programs and see how they do it, and then see how they compare to what we do, and ask like, does it make sense? What's our excuse for being slower? And I can show an example of that from a project that this is inspired by. So if I go to this blog post, there's a flame graph somewhere. Yeah, so this is the before and after of doing a lot of fetches at the same time. And what's interesting about this flame graph is that Git is generating data, and then it has to pass through Git lead, has to pass through Workhorse, and pass through Nginx, and then it goes out the network socket. So really GitLab, GitLab, Workhorse, and Nginx are doing the same job. They're just copying bytes from between sockets or file descriptors. Look how small Nginx is, and look how big Workhorse and GitLab are. So that for me, it took a long time for me to realize, like, wait a second, what is our excuse for being this much slower than Nginx? But how do you find out that this is possible? Like, it's luck that Nginx happens to be sitting here doing the same job as these two guys, and I can be like,
Right.
Nginx does a better job. Why? Well, the thing is, if you look here at Nginx, then this is system call. It's reading from a Unix socket. This is writing, and this is waiting for work to be available. And then there's very little time that is not spent waiting for the kernel to do stuff. And that makes sense if you realize, if you think of it, that Nginx's job in this benchmark is to copy bytes. So it shouldn't be doing anything else. So in that particular case, the fact that these other processes are doing something, it's like, here we're writing bytes. What's this? Why does this have to be here? That, but it took me a long time to realize, like, wait a second, this does not have to be here, and we can actually get rid of it. That was, for me personally, that was quite some steps to go through in my thought process, because when I started looking at these profiles, I would just always notice, like, yeah, okay, there's the garbage collector. That's normal. It's supposed to be there. Well, only if your program is inefficient. Going back to the toy, what I actually did, I wanted to demonstrate this without having to go into that flame graph. So I made an alternative implementation of my DD Dev Zero thing, where it's an HTTP server. So there we just use the Go standard HTTP library, and we make a function, and it takes the total amount of bytes we want in the block size, and then it calls this zero fetch function into the writer, the HTTP response writer. So this is sort of, and this is actually a technique that I want to encourage people to use. Is if you think something might not be optimal, try to re-implement it in some, and just cheat, but try to do something that essentially does the same work and see how fast that is. If, like, say you can do the job by shelling out to a binary, and maybe we're not allowed, or for practical reasons we cannot use that binary in our implementation, but if you're just exploring, just cheat or use things that you're not supposed to use and see how fast they are. So in the case of those problems with gRPC throughput, I couldn't really go and say, well, let's just turn Gitly into an HTTP server. Like, that's like 120 RPCs, and that's a crazy amount of work. But I could ask myself, like, what if this little part of the problem was written differently, and can I go faster now? And yeah, so if we run the benchmark against this, so to do that, let's see, I did that with curl in the README. So let's see. Yeah, so this command does 50 gigabytes with curl. And if I run that, it runs in 2.3 seconds. And the first one ran in longer. Yeah, 7.5. So that is that's suspicious. And then you can start exploring the problem. Yeah, one thing, let's capture a perf profile to see what happens in this case where we download 50 gigabytes with curl. And I mean, it is pretty obvious that we're downloading these 50 gigabytes because curl says so here. It's not like it's cheating and not doing the work. And first I'm going to make another test function that does this. Oh, it's repeatable. Where is it? And if you're using, this could also be a benchmark function in a Go process, in a test suite, right? Like, it doesn't have to be a shell script. It just happens that for this particular case, shell script is a natural choice. So if I run this, it does the thing again. That looks good. And I'm going to do this perf record from the outside because that worked better last time. And I run the workloads. Let's look at that. What's the date? It's I shouldn't forget what month it is. It's 26, and then this profile is from 1615. There we go. Okay, so this was doing the same work. And you can see that, by the way, when you use perf, you see these swapper things. That means the CPU is doing nothing, because here it says halt. So here the CPU spent much more time doing nothing. And this HTTP0 process used 233 samples. And here the server used 1150 samples. So that is four and a half times as much. And curl used 127 samples. And just like in the other example with Nginx, you can see curl is doing a system call. It's waiting for data. It's doing a write. And it's doing some funny stuff here. So curl is actually doing some other stuff. Not sure what this is. Maybe it's the progress messages. Yeah, and I can also profile this with just with preprof. So then I need to say bin preprof records on port 8080, because that's where this server is listening. And I want to do that for 10 seconds. Oh, oops. This is broken because of plan 9. I need to do this again. Plan 9 has a date function that has different syntax. So now it's putting spaces in the file names, and now it's breaking my shell script. Because the shell script creates a file name without any spaces in it, if you're using the Linux version of date. And now I talked too long. Sorry. Do that again and start the benchmark. So now we can open the CPU profile for this directory. Sorry, not this. And click View Flame Graph. And we compare this one. Of course, it's upside down. That doesn't help, but you should see that this is more or less the same shape, right? There's this little one, and then these two bigger ones. I wonder why the order, is the order the same? Yeah, first writes. Sorry, this is a write. Why are there two writes? There are two towers that do writes, and there's a little tower that does reads. So there's flush, no flush, and read. Flush, no flush, and read. Yeah, well, it's really the same shape.
Nice.
Yeah. Now, another thing that I think is a fun exercise is, so now I have this theory, like, I wonder if the problem is that, so where's my other profile? I wonder if the problem is that we're doing all these memory allocations, because you can see here, there's these make slice things that are allocating memory, and everything has to be garbage collected. So what if we make the HTTP server bad by doing memory allocations? Like, does it slow down? That's something you can try once you have a toy. So I prepared that. Let's see, because I added a writer that gets a byte slice, and then for no good reason, it makes a new byte slice and it copies, and then it writes that. So you would never use this, but it shows the what can go wrong. So let's put this around here. And let's see if I still have this is the correct command. Let's run this. I think it's already slower. So this took 4 seconds now, and before it was 2.3. And now we can also open the profile. And it's starting to look more like it because we have this GC thing going on, but it's still not as bad. This is 6.14 seconds. And on this one, it was 14.15 seconds. Oh, another thing that is interesting to look at is look at this 14 seconds that appears up here, right? I know that the profile ran for 10 seconds. So this means that the process on average used 140% CPU while this is happening. And you can also see this with HTOP. So if I would go into this box, run HTOP, then you see well, it goes by too soon, but you see a lot of active, like the bars are big. And before I broke the HTTP server, the bars would have been much smaller. So it's still not slow enough. Go ahead.
Yeah, just to understand a thought process of adding like a buffer here is to mimic how gRPC copies things, right? Like you're adding the
Yeah,
buffer. Yeah, okay.
yeah. So my theory is that those allocations are bad. Okay, so the other thing is I spent time reading the source code of gRPC, and I know that they allocate buffers, and I have no why, but like, is it a problem or not? Like what even happens? And by another thing you could do, of course, is to modify gRPC and say, well, let's not allocate those buffers. The problem there for me is that gRPC is a complicated library, and I don't know how to do that without breaking it. So I'm trying to approach it from the other side as to build confidence into what the problem might be. So another thing that I see in this thing, so that BG scavenge, that is garbage collection, sweep. There's also this, and I don't know enough about the Go runtime, but find runnable to me sounds like it's doing context switching. So it's going back and forth between Go routines. And I think we can actually see that if we go into the send message. So let's see. This is a mem move, make slice, that's allocating. Message header, this is also allocating, and here's the transport. And so this is doing a non-blocking send on a Go channel. So this looks very different in the trace, right? Like if you write Go code, like the little arrow symbol is a send, and if you have a select where you can say send if the channel is ready, default do nothing. That's called a non-blocking send. So that's like 4 or 5 lines of Go code. But when it's running, it translates into NB send, non-blocking send. So we can also see this is sending on channels, and footex means that it's doing a mutex, like a Linux mutex. So it's going back and forth between channels. So maybe we can also add that and see if we can make the HTTP server slower, which is ridiculous, but just out of curiosity to see if we can get a profile that looks similar. So I made another writer that spawns a Go routine, and it creates a channel for the request and the response. And the write function takes the byte slice, sends it into the channel, waits for the response, and returns the number of bytes in the error. And this Go routine, yeah, does a select, it waits for those things, and if the context is done, it goes away. So let's add this one to make things even worse. There. So before it was 4 seconds, and if we run the benchmark now, what am I doing wrong? Oh, CTX doesn't exist. That's r.context. Yeah. We're definitely slower. 9.4 seconds. So now we're actually worse than gRPC. So we're doing something pathological. But just for fun, let's see if we can record this. So 9.4, that's very close to 10. So I'm going to record a little longer. Let's say I'm going to record for 15 seconds. Oh, that's not, I'm still in the server. Stop. Go again. Another thing I found useful is once you have a benchmark, you know what the slowest thing is, to sort of pick values in the request size and the benchmark time, so that the slowest thing or the slowest version of the code fits in the window, but use the same window for every profile, because then if you compare them side by side, they're comparable. Because actually you don't have this problem with the Go runtime. You have this problem with perf, because perf will show the CPU idle time. And if you run your benchmark for 1 minute, then there's all of a sudden a lot more idle time, and then the whole graph on the left looks squished because there's more time doing nothing. But the Go runtime omits the time doing nothing. So it doesn't matter if you change the time. Okay, open this one. CPU, this guy. Yeah, well, you can see it's different, right? Because it's not doing a non-blocking send, but it's starting to become slower. So for me, this builds some confidence that the switching between Go routines and the memory allocations are probably the source of the problem. This is a demo. This is a little artificial, but the way on that project I mentioned, where there's a link to the blog post, I made a demo app that you can actually git clone from. So then I could just see, hey, is my git clone faster? And then when that was faster, I really started thinking, how can we go around gRPC and not do this? Yeah. Something I didn't prepare and I won't do now, but that you could try with this is to see the impact of latency. If you do one really big request on the server and a lot of small requests, because you can make the total size small, then you can see what the latency is if you just do small requests or if you add one really big request. And what I expect to see is that if like you do a bunch of small requests of 128 bytes and you add a big request of 5 gigabytes, then the 128 bytes requests probably slow down a lot, because at one point they'll slow down because the garbage collector makes everything worse. Yeah, with a toy like this, you can maybe see if you can reproduce that or not, because that's what we saw. Again, that's what we saw in production, where we started to send more data through gRPC, and at one point, unrelated gRPC calls that had nothing to do with the data transfer were all getting slow. And that was probably because of the garbage collector. Okay, it's been an hour, so I think we should wrap up. Or I'm going to stop throwing new ideas at you. Thank you for listening for so long. Any questions before we wrap up? All right. I'm going to stop the recording. I'll upload it, make it public, and I'll put a link in this repo, and I'll link back from the recording to this repo. So if anybody finds this, you can play with this stuff or try it out yourself. Yeah, well, thanks again for joining, everyone. And yeah, that was it. Now, how do I stop the recording? Why is this?